Log on, tune in, find out. Another good idea from Cambridge.
Microphone. Turn on the microphone. Is there a red light? It's on the top. There's a little switch on the top.
Oh.
Then you should see a red light.
Yes, yes. Okay, thank you very much. I'm going to talk about, I think it was called Postnikov stability of complexes. And this is joint work with Georg Heine. Okay, so the talk the talk has three parts. One of them will deal with classical stability, and then we'll have another part on the complexes, and then I hope there will be a third part about applications. Okay, so we start with the classical story. Okay, so I mean, very classically, so maybe 6 years ago, this would only work for curves, but now we can do it for any polarized variety. So let this be a polarized variety. So this is projective, and H is an ample or maybe very ample divisor. And then we can then we have a notion what it means for a coherent sheaf to be semi-stable or stable or slope semi-stable or slope stable. Maybe let me write it like this. I assume that actually everyone knows what a stable sheaf is. I can say something about it, but I have the impression that this would bore more people than it would do good. So I won't say anything about it. But we'll see a little bit of this, of course. Okay, so we have this, and yeah, so there are a number of reasons why people have studied this, and let me give those. Okay, so one reason is that if you're interested in moduli spaces and you want a moduli space of sheaves, then all coherent sheaves turn out to be too much. But if you restrict to semi-stable sheaves, they form a bounded family, and it's much more reasonable. So semi-stable sheaves with fixed Hilbert polynomial. They form a bounded family, which just means there is a scheme of finite type, and you can parameterize all of those. Form a bounded family. So this theory usually goes by the name of Mumford-Castelnuovo regularity. So and another one is a stable sheaf has. I mean, so I assume that we work over C today. Okay, so there's. And that's the simplest case. So a stable sheaf is simple in the sense that the endomorphism ring is just the scalars, which makes it much more easier to track these moduli problems. So small automorphism groups. So I just write stable implies simple. And simple in the sense I just described, not in the algebraic one. Okay, and these two are somehow relevant if you want to construct moduli spaces. I mean, of course, you can also construct moduli spaces in much greater generality, but if you have these, then the theory becomes nicer. Okay, and then there's more. So you can treat semi-stable or stable sheaves as building blocks for all sheaves using the well-known Harder-Nara-Siemann and Jordan-Höller filtrations. Okay, so all of this is standard, I think. So there are books about it, and it's well known. what I want to report about today is essentially a generalization of a great idea by Faltings. So I'll give the good idea by Faltings first. I mean, this is really something that can stay on this blackboard for the whole talk. So Gerd Faltings, I think 1993, and he saw that there is a cohomological description of semi-stability for curves, and this is what I'm going to tell you now. So let C be a smooth projective curve. And then Faltings has shown a sheaf is semi-stable. I mean, obviously for a curve you don't worry about polarizations, and there's also only one type of stability. If and only if there is another sheaf, maybe not zero, such that the tensor product of E and T has no global sections and no first cohomology. Okay, so in his article, Falting does much more. So he's concerned with principal bundles of a curve and connections on them, and this is just the first part. But I really like this bit, so I would also like to say something about the proof. So the proof has an easy and a hard part, and I cannot fully prove the hard part, but only give an indication. But I can do the easy direction. Yeah. The easy direction is the one where you have this non-zero testing sheaf T with this property, and you want to show that it's semi-stable. Okay, so suppose we had a destabilizing subsheaf.
Is E torsion free or something?
Yeah, let's say bundle. I mean, the result would be true otherwise, but then we would talk about torsion sheaves on the curve, and this is maybe not so interesting. So, I mean, the content is for bundles. Yes, then you can take T a point, but it's more interesting to restrict to bundles. It's still true for points, but not so interesting. Okay, so suppose we have a destabilizing subsheaf, so that just means that the slope of the subsheaf is bigger than the slope of the original sheaf. So this is a subsheaf which violates the definition of semi-stability. Okay, and then, well, we have this T. So we want to bring this into the picture, and the slope of a tensor product is just the sum of the slopes. Okay, and now we can use Riemann-Roch. So I believe that the formula for Riemann-Roch is given wrong in all the books. It should be given as follows. But this is the standard formula, of course, just divided by the rank. Okay, and so we apply this in this case, and then we get the Euler characteristic of E prime tensor T over the rank is bigger than the same for this, but here the Euler characteristic is 0, because by assumption both H0 and H1 vanish, so in particular the difference will vanish. So I can write in small because this is 0 anyway. Okay, so this is so I have two assumptions over there, and here I use one of them, so to speak, that the difference is 0. Okay, and this means that this Euler characteristic is positive, so in particular, because we're on a curve, there must be global sections. Okay, the Euler characteristic is 0 on the curve, there must be global sections, but this means that then there will also be global sections of the big thing, and this violates the first condition over there. So cannot be. So for the hard direction, well, we have to get this bundle T out of somewhere. So we are looking at bundles which at least have the correct Euler characteristic property. So we consider bundles of rank PR, where R is the rank of E, and degree so where P is some natural number, R is the rank of E, and D is the degree of E. Okay, so yeah, we want to test bundle T with those numerical invariants. If you now apply Riemann-Roch, then you will see that at least the Euler characteristic of E tensor T is 0. So that's something. Okay, and now we would like to have a T such that also the global sections vanish. Yeah? And this is so this is generically true, but you have to do something for it. In particular, the P, you may be willing to go up with the P. Yeah. So. Okay, so let's look at the, so E is semi-stable, so I have a moduli space like this, and let's look at the subset, tensor T, of course. Let's look at the subset where this does not just have zero Euler characteristic, but actual non-vanishing H0. Okay, if this would be a proper subset, I could take something in the, well, yeah. So this is something like a generalized theta divisor. You will see a more proper theta divisor later. Okay, and the point is that if you choose P to be very big, so you have to really allow yourself to go up from R and this degree. If you choose P big and T in generic. Yeah. So not any T will do, but if you choose P big and T generic, then this will actually be a divisor. So then this is a divisor. And not just that, it's an ample divisor, it's a polarization. Okay, and then you have enough flexibility to choose it in a T adapted to the E such that both H0 and H1 vanish. So the non-vanishing is then a closed condition and there's an open subset of the others, okay? But this requires actually some work. Yeah, so maybe here I can write down. So once you know that there is such a T, such a testing sheaf T that allows this, then you can wonder if you can get a more explicit handle on this. And this is possible. Popper has given effective bounds on the degree and the rank of this, okay? These numbers become a bit clumsy. I don't want to write them down, but you can say at which rank you can get such a T. Effective version by Popper. Okay. So maybe some small examples. Yeah. So I really like this idea of this orthogonal sheaf. So I'll give some examples first, and then we'll try to generalize this. So what's the simplest thing you could start with? Maybe the structure sheaf of the projective line. Then there's only one sheaf you can take, and so there's no choice at all. It's this one. If the genus is higher, then there's a full complement of the theta divisor of them. Yeah. So this is the subset of line bundles of degree g minus 1 which have global sections, and this is a polarization for this Jacobian. Oh, polarization. And so this is very classical algebraic geometry. So that you can take the T to be in the complement of this.
Are you saying that T is equal to OFC? I'm not clear.
Say again?
Is it T that's OFC here or what?
No, E is the success sheaf, and T is anything in this complement. For example, on a elliptic curve, you would take any line bundle of degree 0, which is not the trivial line bundle. Okay, I mean then it's yeah. So then it's the complement of a point, because the Jacobian is only a curve. But in genus 2, you have a surface full of these and take out one divisor. Okay, so T is anything outside this theta divisor. So this is the classical theta divisor, yeah, and this is somehow a generalized version. Okay, and maybe one more example. So then now if you've seen this, you could get bold and ask, well, what is for higher dimension? So maybe one of the first things to look at, let's take the tangent bundle or cotangent bundle 2p2, and then you can take, now I have two t's. So this is the tangent bundle. Yeah. Then you can take this line bundle. I mean, you can see that this is semi-stable from the Euler sequence, and you can also see from the Euler sequence that this works. Okay, and then well, so why is Faltings good? For example, because you can rephrase it as follows. Yeah, so Falting states that these two cohomology groups vanish. This is the same thing as saying and this is the same thing as a Horn group and an X1 group, and this I can rephrase by saying that the dual of this testing bundle is orthogonal in the derived category. Okay, and this is something that I really like. And the question is if this idea can be generalized to high dimension. And I say it can in a meaningful way, and I'm going to present this now. Okay, let me see if I've forgotten something crucial. Oh, it doesn't look like it. Okay, now stability for complexes. Okay, so this is the definition is a notion of pure homological algebra, and then I'll try to convince you that it actually makes some sense. Okay. So let D be a C-linear, Hom finite, triangulated category. I mean, I'm exclusively thinking of D of some variety X. Okay, but I mean this is a natural setup, and then we choose some objects. These are objects, and we choose numbers, or we fix numbers, and the J is in Z, and the I runs from D to E. Okay. So I have a finite bunch of objects, and I have these numbers, and this together I call a Postnikov system. And because there will be so many Postnikovs later on, I just abbreviate to P system, okay? Yeah, this is somehow in the abstract setting my generalization of the line bundle L. Yeah? So when you talk about stability of sheaves on a variety, we have to choose a polarization, and here I have to choose a lot more. But this is the stability data, so to speak.
These would all be powers of the line bundle.
No, it will be no. I mean, in simple cases, yes, but in general not. I mean, it's also not at all clear that this definition is the best one or even a good one, but at least it does something, and I will tell you after I have finishing the definition, or maybe after finish erasing this. Okay. Definition. It might have been smarter to start the definition over there because I need a diagram. Okay, an object of this triangulated category is called p-stable with respect to this datum if there are three conditions fulfilled. So the first is a bunch of numerical conditions. Okay, I can look at the Hom spaces from these objects up there to the new object A, and also at the higher Hom spaces, and ask what their dimensions are. There should be the numbers fixed over there. The second one is there should be differentials on half of these C's. Of course, all differentials are called D. Yeah. So now the differential means that D squared is 0 at every step. So now this is a complex of objects in a triangulated category. So I would like to form the total complex but can't. So the only way out I have, at least as far as I know, is a Postnikov system. So this is also why this is Postnikov everywhere, such that there is a convolution. So for this convolution, I should draw a diagram somewhere. Okay, I mean, if you know what a Postnikov system is in the convolution, you don't have to do this. But if you don't, then I draw the diagram for you. Something's wrong. Already know something is wrong. How can this be? Okay, so you have this complex of things, of objects, and you want to take cones at every step. Yeah? So this step is easy. You can also take a cone, but already here there could be a condition. You look puzzled. Did I get my arrow wrong?
There could be what?
No, they're okay. No?
So what do you say? Already there could be what?
So this is trivial. Here I just take the cone of this map, which is just this D. But here it's not clear if and how I can continue. Yeah? So this is a condition on the whole thing. And if I can keep going all the way, then I call this a convolution.
Sorry, can I just ask? I'm a bit confused just by the indexing. I mean,
Yes, I can imagine. Yeah, the indexing is not very clear.
Yes, these objects originally went from C on the top blackboard.
Yes, this is the positive half over there. You see, the D is negative, and then I go to D0, and then there comes some positive part. And it's not clear if this is a good way of presenting things. Probably not. This is the positive part written down from highest to 0. It's a bit of a mess. Yeah.
So what does the condition
2 on stability or d-stability of 8 has to do with object 8?
You will see, because there's a 3 is missing.
Is decomposed D 0 in the derived category?
Sorry, say again?
Is decomposed D 0
Yes,
in
this-
the derived category?
Yes. This is what I mean by these differentials.
Is D allowed to depend on A, or is it an absolute thing?
No, it's really like this. You have these given, and then you can choose these maps such that they form differentials, and that you can fill in this diagram. Okay, and then then there's this assumption that this convolution exists, and then I want that this to be orthogonal, just like in Faltings. Okay, so what? So we had T before. Now this is K-like convolution. Okay.
Sorry, I haven't understood this. These T's are not meant to be the homology of this kind of complex, right?
No.
They're meant to be the complex up to degree E minus 2 or something.
I mean, if you imagine that you start with an actual complex of sheaves, yeah, and then you can take this to be the full complex and split off one component each time. So you start with the sheaf here, length 1 here, length 2 here, all the way, and then you would make your complex longer and longer. So you should think of this as this should be something like the total complex of this thing.
I see.
Yeah.
So
I
if
mean,
there's some DG enhancement where D squared is really 0, then you just do the obvious thing.
Yes. Exactly. Yes.
So there's some massey product obstruction to this thing.
Yes, but I'm not familiar with this. So in the cases that we use, things are actually much more simple. So for example, if all of these are sheaves, then this K will just be this as a complex of sheaves. Okay, so this is what you expect, and this is also.
What's this cross through the arrow mean?
This is the degree increasing arrow.
I see.
These are These are commutative triangles, and these are somehow distinguished. And this is the arrow that increases the degree. Okay. I mean, this is a purely homological algebra, and then so after everyone agrees that this notion of Postnikov system exists, then you can write it down. But of course, it's not clear what it's good for, and so I'll try to tell you. So not here, maybe there. Okay, so there's a theorem. So this is the thing we were after. And yeah, I mean, let's take the simplest case. X is smooth and projective. You can reduce the smoothness a bit, but let's not worry. Oh, I should choose the polarization. And I fix the polynomial. Oops. Yeah, then there exists such a Postnikov datum, so such a bunch of complexes or sheaves. In our case, it will all just be sheaves and numbers. Yeah. So then there's a p datum such that an object E in the derived category of X is a sheaf, so is concentrated homologically in degree 1. And as a sheaf, it's slope semi-stable with respect to H. And its Hilbert polynomial is the given P. if and only if this object is stable with respect to this p at atom. Okay? I mean, I believe that this definition is a bit, it's too general, and one could restrict it, but at least it's good enough to have something like this. Okay? You can formulate classical semi-stability of sheaves in homological terms like this. Okay, I will tell you why I got into this in the first place, but before that I should maybe two or three things on this alone. So something similar holds for Giesecke stability, so restricting to slope is not really crucial. So similar for Giesecke stability. But it is crucial to have semi-stable, not stable.
Are you saying this p stability is forcing E to be a sheaf? Is that what that is that my correct?
Yes, this I mean it says you can choose this Postnikov datum such that it forces the E to be a sheaf. Yes. Of course this only works because we are not just interested in sheaves, but in sheaves of a fixed Hilbert polynomial. Otherwise you would have no chance. You see? It's a sheaf of given Hilbert polynomial. I mean you cannot expect a bunch of conditions in terms of Homs alone that make a complex a sheaf. I mean, this is out of the question. But here we have this P, and then this is why you can do this. Similar for Giesecke semi-stable. Okay, so maybe I can use this one.
If you're in dimension n, can you restrict this E to be n or something? There's a number of terms in that.
Ah, yes. Yes. But yes, you can. But in fact, there is a result by Alvarez, Consul, and King, and they tell you so that they were doing something else. This is the functorial construction of moduli spaces article. They were doing something else, but in particular, they show, of course, not in this language, that in the Giesecke semi-stable case, you can always restrict if you want to E equals 1. You can have really short guys of these. Yeah, so I'm saying so. This definition is probably way too general, but at least it works. Yeah. So okay. Maybe I should say something about these conditions first. So this nails down the numerical properties of the object A. Okay. For example, you can prescribe a Hilbert polynomial using things like these. Okay. And then this is why we set it up. After all, this is Falting's orthogonality condition. Yeah? Then perhaps it would be better to split up these C's into the negative left part and the positive right part. And the positive guys are the active parts, so to speak. Only they play a role in this Postnikov system, and the other ones are only used for this. Yeah, so maybe there's a better way to.
Can you confirm? You just said that Alvarez, Consul, and King confirm you can just work with E equals 1, but then the second part of your definition seems to be superfluous.
Yes, then this is not necessary. I mean, in the curve case, there are cases where just one is okay. I mean, this is what Falting does, right? There's just one thing that's necessary in the curve case. Yeah. Okay, but I'm not aware of something like Alvarez, King, Consul, King for mu semi-stable. Okay.
And what are the objects C that do this for me? I mean, are they sheaves?
Yes, they are.
An ample line bundle?
Yes. Ample line bundles and sums of those, so the rank can get very big if it needs to be. And not just line bundles, but very simple vector bundles made from line bundles. Okay, so there's the first part. So first of all, you want your complex E to be just a sheaf. And so there's a homological sheaf criterion. And we can use these passive C's, those on the left. Yeah, such that this condition forces E to be a sheaf of a given Hilbert polynomial. Okay, and then the way we prove this is by induction, and you want to cut with another hyperplane, which is very general and restrict semi-stability, and this is possible by meta-Ramanathan, or I mean, you want to do it in an effective way, so you have to use Lange. Yeah. So in the end, you end up with a very, very movable curve, which is the intersection of a number of very ample divisors, and then you can get back to Faltings. Yeah. Perhaps that's clumsy, but this is how we do it. Yeah. Okay. So and then there's a little time left for applications. So I can tell you why I did this, and I think I can also tell you why Georg did this. And then time's up.
So the set of kind of p-stable objects, can you see that it's naturally a stack or something? I mean, can you see that it's separated or proper, or does it have a one parameter?
What you can do is no, you can get a trace of this moduli something if you look at all the d's that you can choose. I mean, in this definition, you can fill the d's however you like. It does have to be a differential, and they have to fulfill this condition. And if you have one of them, then you can deform them, and this gives you so this is some big projective space where all these d's potentially live, and then a subspace in there where these that are actually allowed live, and this gives you something like a trace of a moduli space, but I'm not aware of an actual moduli space here. Yeah, so this is somehow not what we were interested in.
Are you talking about a moduli space of the Postnikov systems?
We were talking about a modular space
I want a moduli space of stable
It
objects.
was one of Falting's motivations to do this, to construct a modular space of bundles without using any geometric invariant theory at all.
Yes.
Can you do this now again for the modular space of sheaves?
This I don't know. So what this can be used for, so I wanted to say something later, but I can do it now. You can use this in order to compactify a classical moduli space with something that is an actual complex. Yeah, so that you have your stable locus, and then you have complexes of length 2 sitting in the boundary, and this is a new compactification. This is what you can do, but we have never really investigated if you can I mean, what happens if you want to form a moduli space of these?
But do you know, for instance, if you have a family of p-stable objects over C star, whether you can fill it in with a p semi-stable object over the origin?
I don't know.
You don't.
I don't know. Well, it should be investigated, but it's only Georg and me and Marcello Ganadara so far, so this has never been done. But yeah. So I really believe that I don't believe so much in this notion of p-stable. It could be too awkward, but I really believe in this idea of Falting. So there must be something to this. Okay, so last part, applications. Okay, so my main motivation when we started this was the following. So back then there was a new article on preservation of stability, maybe every week, or at least every 2 weeks. Okay, and this, so I'll explain what this means. And this is from one point of view very natural, because you are interested in birational maps or even isomorphisms between moduli spaces, so this is good. But from the point of view of the derived category, it's perhaps not so natural. So this was my motivation. So let's say different point of view on preservation of stability. Okay, so what is this about? So suppose you have an equivalence between derived categories of two smooth projective varieties, and then you can ask the following question. If you have something over here, so that goes to a shifted sheaf over there, then this is good, because we can talk about stability of sheaves. So we call this WIT, weak index theorem, if its image is a shifted sheaf. And actually IT, so without the weak, if this is locally free. Okay, now you can ask the following question. If you start with a semi-stable sheaf over here. And it's, say, so it's WIT is the image, which is then the shifted sheaf, also semi-stable. Okay, and then generally the answer is of course no, but I mean if this equivalence comes from geometry, then surprisingly often the answer is yes, and this is what goes under the name preservation of stability. I'll give you one specific example where this works. Okay, so people do this, going. If you have this, then you can expect this to hold for whole families of these, and then you would get at least a rational map from some moduli space on the left to the moduli space on the right. Yeah, so the idea is to use Fourier-Mukai transforms in order to construct rational maps between moduli spaces. Sorry. From Fourier-Mukai transforms. Okay, so and the thing I didn't like so much about this is that you have to plug in this here. Wouldn't it be much more nice if you had a notion of stability for complexes, and then such that the thing on the other side would be automatically semi-stable as a complex, and then you have the preservation of stability for free, so to speak, and then the question turns into whether this becomes a sheaf and whether what a new transformed stability condition is on the other side. I mean, of course, it's the same question, but somehow it's a different point of view on this. And I can give you one example. So we only bother to work out one example. And this is an abelian surface. So polarized abelian surface. If you have an abelian surface or an abelian variety, then there is the classical Fourier-Mukai transform by Mukai. And you can use this. So we use H in order to define what it means to be semi-stable over here. Yeah, so something is semi-stable here if it is semi-stable with respect to H. I want a natural polarization on the other side, and I can get it using the Fourier-Mukai transform. So this is a polarization on the dual abelian variety. Okay, and then that's the following result. E is stable, degree of E is 0, rank of E is bigger than 1. I mean, if it's 1, then it goes to a skyscraper sweep of a point, so we want to exclude this. And then this thing is IT1, which means that so there's, if you push this forward, here this contains a push forward, then there is no 0th direct image, but there's a first direct image. So it lives in degree 1. And so this is an actual sheaf. This is now mu semi-stable. I don't really know who to attribute this to. So this is in the book by Hernandez Riperes and Hugo Bruzzo and the others, and I think it's also proved by the Spanish, but I'm not fully sure. So in any case, so we are able to reprove this with the philosophy I explained to you before. Yeah? So we have something over here, and we want to show it. So and this is so we choose the Postnikov system. This captures the semi-stability, which is rather simple. So I think this is Georg's thesis. So this is a very simple Postnikov system. Then you move this over here, and then something that was semi-stable for this p-stable for this will automatically be p-stable for the moved p-datum. I mean, the p-datum is completely, it is abstract nonsense. You can of course move it on under an equivalence. Yeah? So you get something that is p-stable here, and now you have to check if this p-stability actually is H hat stability, and the answer is yes. Yeah, so this is one example where this works out. Okay, and then maybe one last application. This is about elliptic surfaces. Or maybe elliptic K3 surfaces. So this is by Marcello Banadara and Georg Hein from last year. Okay, and they look in an elliptic K3 surface with the section. And they have some condition on the singular fibers. They should only be nodal. Okay, and yeah. So then there is the dual elliptic fibration, which in this case, by the presence of this section, is actually isomorphic to the old one. So dual elliptic fibration. And this classical Mukai transform works fiberwise, so you get a fiberwise equivalence. Okay, and now so the story is old, so maybe I didn't write down from when the conjecture is. So Friedman started investigating this, yeah, and so the goal is study the birational geometry. I mean, the goal is similar to the one we had before, birational geometry of these moduli spaces. Okay, and yeah, so you can do this in several ways, and Banadara Hein do this using these this p-stability, and then Friedman came up with a conjecture. I think I should be able to provide a year. 85. Okay, and the conjecture goes as follows. There are some numbers now. So we look at the moduli space of rank 2 sheaves with a polarization given by the section minus some number, the fiber. So this is the section and this is the fiber. And then C2 is 1. Yeah. And then this is birational to Hilbert scheme. So let's check that the dimensions make sense. So this has dimension 2t. Yeah. And here you have to compute the square of the Mukai vector, and then minus 2. So this gives 2t. Yeah. And then you have another 2, but you subtract. So in this definition you have minus 2. Yeah. So this makes sense. So they both are 2t dimensional, and this is also smooth and projective. Projective 2t dimensional. Yeah. So you get from this you get a birational isomorphism between these two, and Friedman conjectured that this would be an isomorphism for all t. So this is the conjecture. Yeah. And I mean, of course, he did something about it. He tracked this for 1 and 2. Yeah. And then he conjectured it to be an isomorphism for all t.
What is the map?
This is a good question. I mean, this does not come directly from this, right? Who asked?
Oh, I'm just asking what the map is.
Yeah, I know.
Why can't you take the Furi-Mackay and then tensor by appropriate alignment? I mean, when you take the Furi-Mackay, you'll get something of rank 1, right? So
Yeah, yeah. So you take a stable sheaf over here. Oh, then you take this phi over there. So I think these two get swapped, right? So this is rank 1. So and then this is the ideal sheaf of something, and then this is.
Should that be the Hilbert scheme of points at H dual?
Yes, it should be. It should be of X dual. Yeah? This is true. This is true. Okay. So I mean, so this is the ideal sheaf corresponding to this. So if you're happy that your Hilbert scheme parameterizes ideal sheaf, then you should be done at this point. Yeah, and then so there has been, I mean, these moduli spaces or sheaves on elliptic fibrations have been studied, I mean, severely. So, for example, by Tom Ridgeland and by Ugo Brutzer and many others. So, I think in physical jargon this goes by heterotic string or something. Yeah.
So the answer then was you take the Fourier-Mackay transform that's already an ideal sheaf up to some.
Yes. Yes, and then you probably have to work out the twist too in order to make it pure. Yeah, and so what Hein and Bernardara contribute to this is that apart from other bits I maybe not mention here, so this is not an isomorphism for T equals 4, and there's something else.
What about T equals 3?
And then there is. Okay, if you go back to the original setting, there's exactly one Mukai vector that can figure as a potential. I mean, so you start with semi-stable sheaves of some Mukai vector over here, and you get something which will relatively be sheaves, so there can at most be one Mukai vector. This is unique, given this transform and the original Mukai vector. So you have this, and then you can wonder when this is an isomorphism, and this is, they call this epsilon for some reason. Epsilon is an isomorphism. They have a criterion. If 2t is less than 2r, so if the rank goes up, it becomes more probable. But here the rank was quite small, and it's a Mukai flop if and only if this t is still bounded. Okay. Yeah. So that's it. I think that it's really worth trying to extend this idea by faulting to the derived category. I mean, we may have got it wrong, but at least we got something out of it. Thank you.
Any more questions?
I have a remark, just to advertise some work that Aidan Schofield did years ago and never wrote up, which was just that in the curve case, if you fix a bundle and look at the category orthogonal to that bundle, so as you said, that's all semi-stable things. That consists of semi-stable bundles, but maybe of different ranks, all of the same slope, but maybe of different ranks. And he proved that there's an algebra. It's kind of an easy proof that there's an algebra such that the category modules of that algebra is equivalent to that category.
I see.
So he thinks of that as some kind of way of making the moduli of sheaves out of non-commutative patches or something. I don't know why that's better than making it out of commutative.
Okay, see.
Well, I mean, I do actually, because I mean, the X proofs between the simples and this actually becomes an equivalence of categories. So the modules of this algebra completely model the sheaves.
And
so I don't know whether that can be done in higher dimensions. That would be fun.
I mean, as you say, he only does the hereditary case, right?
He only does what?
So only curves.
Only curves.
Yeah. So this is, I mean, so the right categories of curves is so much simpler than anything else. But I mean, one can try to do something. I find that this approach with restricting all the time to one codimension, I mean, it's geometric, but also very clumsy. But I don't have. I mean, it would be much better to have a direct way to get the orthogonal thing, the k, to the east, right? But we don't have one apart from restricting until we have a curve, and then we find something that lives on this curve, and then this is orthogonal to this family of semi-stable sheaves. There should be something better. Yeah, there was a question.
Maybe I'll ask. The most naive thing you could say about faulting is you could just take T to be keep E to be an object-derived category and T to be another object-derived category, and have this all Hom 0.
Yes, but of course, this is way too general. I mean, then you get.
So this is a worthless notion.
I think so. Yes, I think so. I mean, of course, this is how you would go and generalize findings by dimension. But I think this is too careless. Then you don't get anything useful. I mean, of course, you could say that our notion of p-system is just as careless. But I mean, so the theorem I gave you tells you that it's not too big because it can capture exactly what it means to be a semi-stable sheaf. The naive thing you start with, it will be too big.
So maybe you could just say, like, what in the naive generalization, what's the first worthless thing about it?
What's the first one?
The first worthless thing about it.
So you think about, well, if you take something like P2 and you take the structure sheaf of O and look at the orthogonal of that, then it's just going to contain loads of stuff. I mean, it's going to contain anything in the category that's made up of O1 and O2. You have this theory of exceptional collection, right? So
Yeah.
you took an exceptional bundle and took it.
There's no hope of making a moduli space or anything like that.
No, this is really too big. I mean, P2 is maybe too small, but if you have Pn, then you have many of them, and then you can even combine them to get complexes.
So what if for like dimension 2 you pick not one, you pick 2 objects and go orthogonal with both of them?
That's kind of what he's doing.
Yeah.
Yes, and
That's kind of what you're doing.
I mean, we started with exactly this question, and then this is where we ended up. So perhaps you can do better, but this is exactly where we started.
Okay, so any more questions?
So what is the Postnikov system for the abelian circle?
Yeah, I can write it down. Also, I have to read it up. So these Postnikov systems have a tendency to be not so terribly beautiful, but I can write it down.
How did you come up with it?
Like I said, I mean you intersect. So this is the reason why. So the bigger your dimension, the less concrete it gets. So this is, for example, the reason why I wouldn't be too happy to replace a surface with something higher. It will work, but it will just get more ugly. So so let me look for the abelian surface case. Okay. So this is on A. So E is mu semi-stable with respect to this polarization, if and only if E restricted to C is mu semi-stable, where C is in this is an ample curve. Maybe you have to go up. So you probably can even make this M effective, okay? And then now you have this orthogonal object. I mean, as I said, this is restricting, but here only once because we go from surface to curve. And then you have to choose some bundles, and you can take line bundles for these that nail down the numerical properties of this. Yeah, so this is maybe half of the work that we are doing. How to write down in an efficient way the passive data that makes sure that your complex is actually a sheaf and has the right Hilbert polynomial. Yeah, but this is, I mean, how to say, the interesting part is of course this orthogonal bit, and this is this. Yeah, it's just you take a very ample curve and that's it. Okay, and then here on this curve, of course, here you can produce something orthogonal other things.
Is this construction by an arbor using ample sequences or something? Well,
yes, I think this is related, but I don't really see how. So I mean, for example, this is clearly not related to Thomson's notion of stability conditions. I mean, this is so Marcello had the idea that perhaps particularly rational stability conditions could be captured with this p-stable system. But apart from this, it seems to be very distant. And what Inaba does seems much closer to this, but I don't see. I mean, we were really trying to have something that allows us to move from the stability in the abelian category to the stability on the derived category, and still go back. And this is why we did this. And I'm not aware of something that is something else that does it like this. So yeah, there should be a relation, but I don't know.
Okay, any more questions? Let's thank the speaker again.